Securing a large language model requires red teaming, attacking the model to identify vulnerabilities before deployment. As safety alignments grow more complex, researchers hit a strict bottleneck. They still rely heavily on manual, human-driven prompt engineering to trigger harmful outputs. Automated jailbreak tools like pair or tap were built to scale this process, but they possess a core limitation. They lack persistent memory. When attempting nuanced social engineering, they cannot retain which tactics were successful across multiple interactions. Without long-term strategy retention, baseline tools essentially guess at random. Against highly aligned models, this brute force approach frequently results in low efficiency and fails to penetrate robust defenses. AutoDAN Turbo is a multi-agent framework built to solve this memory and learning deficit. It operates as a lifelong learning agent, designed to discover and remember complex jailbreak strategies from scratch without human intervention. It operates entirely in a black box setting. The framework requires no white box access to the target model's internal weights. It only needs to process the model's textual output. This suggests that the next stage of red teaming must move beyond trial and error, focusing instead on identifying the specific psychological tactics that modern safety filters are susceptible to. To test this capability, we look at HarmBench, a standardized proving ground for evaluating automated jailbreak tools. This radar chart plots AutoDAN Turbo against baselines across open and closed source models. Against GPT-4 Turbo, it achieved an 88.5% attack success rate, bypassing standard safety alignments. Across all tested models, it maintained a 74.3% average performance increase over the runner-up. The data shows a consistent ability to compromise state-of-the-art models. To understand why, we have to look at how the framework extracts and reuses linguistic strategies. AutoDAN Turbo's performance is driven by an autonomous pipeline that extracts linguistic patterns, converts them into vectors, and systematically applies them to new requests. The architecture begins with an adversarial relationship, an attacker LLM and a target LLM. The attacker LLM is fed a specific malicious request and is tasked with generating a jailbreak prompt, labeled P. The target LLM ingests prompt P and generates a response, R. In early iterations, this response is usually a refusal. To evaluate the response, the system introduces a third agent, the score LLM. The score evaluates the target's response and assigns a numeric score on a strict 1 to 10 scale. A score of 1 represents a complete refusal or a response entirely unrelated to the malicious intent. A score of 10 signifies complete compliance with the harmful directives of the request. This loop generates thousands of raw attack logs, but at this stage, the system has only collected data. It has not yet extracted any reusable intelligence. To utilize these interaction logs, the framework must convert raw text into formalized knowledge. This conversion is handled by the fourth agent, the summarizer LLM. The summarizer samples 2 logs from the data and looks for instances where the score of round I+1 is higher than round I. It then performs a delta analysis, comparing the linguistic differences between the 2 attacker prompts to deduce what caused the compliance score to increase. The summarizer outputs its analysis as a JSON object containing 3 elements: the strategy name, its definition, and an example prompt.
For example, it might identify a strategy like expert testimony and user experience combo by analyzing a successful prompt regarding bacterial cultivation. To maintain a clean database, the system provides the summarizer with a list of existing strategy categories to avoid duplicating previous definitions. Once verified, the new JSON object is appended to the permanent strategy library. This allows the framework to autonomously convert trial and error interactions into a structured programmatic data library. Once a library exists, the next challenge is retrieval, knowing which specific strategy to apply during a live attack. Attempting to retrieve strategies based on the attacker's own prompt often results in inefficient guesses that do not reflect the target's current behavior. AutoDAN Turbo addresses this by using the target LLM's response as the retrieval key. The text of the model's refusal is mathematically transformed into an embedding vector, denoted as ER sub I. This vector is queried against the keys stored in the strategy library. This process matches the specific phrasing of a current safety refusal with strategies that were successful against similar refusals in previous rounds. The matching results are then sorted by their historical effectiveness to create a retrieved strategy list, labeled gamma. Anchoring the search to the victim's own words allows the framework to contextually adapt its attack vectors to specific safety filters. The retrieved strategy list gamma dictates how the attacker LLM is prompted for the next round. If a retrieved strategy has a historical score greater than 5, it is considered highly effective and is fed to the attacker for direct reuse. If the highest strategies score between 2 and 5, the system instructs the attacker to combine them. This creates an algorithmic evolution, forcing the attacker LLM to synthesize new tactics from moderate successes. A fallback state occurs when the target remains resistant and the retrieved strategies fail to score above a 2. This triggers the system's find new protocol. The failed strategies are fed back to the attacker with instructions to avoid them, forcing the LLM to approach the target from a different psychological angle. This tiered feedback loop ensures the framework constantly iterates, mutating its tactics until it breaks the target's safety filter. These components form a closed-loop pipeline that operates autonomously from initial generation to strategy extraction and retrieval. The strategy library is modular, meaning human-engineered tactics from academic papers can be manually added in a plug-and-play JSON format. The system can operate in a continual learning mode, where the library expands during an attack, or an off-the-shelf mode. In off-the-shelf mode, a populated strategy library is fixed and deployed immediately against a new unseen target model. This transferability is supported by empirical evidence. A library built by attacking open-source models like Llama 2 can be deployed off the shelf to effectively compromise closed-source models like GPT-4. While early automated red teaming relied on simple prompt variation, this framework demonstrates that structured memory is essential for bypassing modern alignment. As safety protocols advance, alignment researchers must account for adversarial systems capable of context-aware strategy discovery and lifelong learning. By converting social engineering into a systematic, vectorized extraction of vulnerabilities, AutoDAN Turbo demonstrates how structured data can be used to bypass current safety filters.